Hey BC students, it's Mr. Martin, and in this video we'll cover geometric series. If you're following along at home, I would recommend that you just watch the video. Don't try to copy what I'm doing first. In the description for the video, there is a link that visually explains how a geometric series works. If we were in a proper classroom, I'd show you guys how we're just basically taking a shape and dividing that, and we keep adding what we divided in each step. That's how a geometric series works. Also in the description, there is a link for a download of this file. You can still find it on my Edmodo page in a folder called Infinite Series. All right, so with the geometric series, we are working with the terms of a geometric sequence. This entire first page is just explaining what a geometric sequence is compared to a series. I'm kind of going to read this, but kind of paraphrasing as I go along. So a geometric sequence is a sequence where we multiply to get the next term in the sequence. In this case, we have a sequence AN in the first, 6 terms are 50, 10, 2, 2/5, 2 over 25, and 2 over 125. And you can see that in each step, we are dividing by 5 to get to the next term, or we're multiplying by 1/5. All right, so the common ratio for this sequence is 1/5, and the first term is 50. The proper notation that we would use for this sequence is 50 times 1/5 to the n minus 1. This exponent doesn't really matter. Sometimes you see n, sometimes you see n minus 1. It honestly depends on what textbook you pick this up from, or how your teacher or professor prefers to write a sequence. The College Board even goes back and forth on this. So it's more important that you can identify the common ratio and identify the first term as opposed to what this exponent stands for. Generally speaking, we're going to use n minus 1. Sometimes we'll use n. It's up in the air. So anyway, like the sequence is 50, 10, 2, 2/5, 2 over 25, and 2 over 125. And then the next term would be 2 over 625, and then 2 over 3125, and so forth. If we were to add the terms of this sequence, then we are working with what we call a series. And a series is just a sum of the first however many terms of a sequence. So if we take this sequence and we were to calculate S4, that means that we would be adding 50, 10, 2, and 2/5. So like down here we have S4 is 62.4 because 50 plus 10 is 60, plus 2 is 62, plus 2/5, which is 0.4. That's going to give us 62.4, or as a fraction, that would be 312 over 5. These sums are what we call partial sums. And if we were to calculate A7, which means that we calculate the 7th term in this sequence, it would be 2 over 3125. And so then we would add that to the 62.4, and we would end up with this value. So, that would be if we calculate it as 10. And so S10 is 62.499936, and S100 is 62.5. So in adding 90 terms to this series, the sum of the series is, it only goes up by 0.000014. And that's because for this series, because the ratio is 1/5, as we add terms to the series, each term that we add is smaller than the previous term. So there's an upper boundary on the sum that we're working with. When a series has an upper boundary, or in this case, we can say a limit, we're going to call that series convergent. And so this first series, AN, it converges because the common ratio of 1/5, that's less than 1. And so anytime a geometric series, the ratio is less than 1, that series is going to converge. Now, in the second example, we have this other series that's 3 4s, then 3, then 12, then 48, then 192. And we can see that in this series, in this sequence, each time we multiply by 4 to get the next term of the sequence. So the way we would write this sequence is 3/4 times 4 to the n minus 1 power. Now, if we wanted to calculate S3, now S is for sum, and 3 is just for how many terms are in the sum, the first 3 terms. So we're going to have 3/4 plus 3 plus 12. That's going to be 15.75. Now, if we were to calculate S5, that would give us 255.75. And there's a way to do this on your calculator. I'll show you quickly. If we press math and you press, you go down to 0 for summation, we do x equals, we're going to say 1, and we're going to just do the first 5 terms, and we're going to have 3/4 is 0.75. I'm going to write it like that, times 4 to the x minus 1 power. And so we press enter and we get 255.75. So what we see is that the sum S3 is significantly less than the sum S5. And so if we were to come back in here and calculate S, we'll say 8. It may blow up the calculator, who knows, we'll see. That's not too bad. But you can see that just by adding 3 more terms to the series, we added about 16,000 to the sum. And so if we came back again and we add, say we add 4 more terms, and so we get up to S12. And so now we get a sum that's 4,194,000. So as we add terms to this series, the sums get larger and larger. And when series do something like this, we're going to call those series divergent because the infinite series grows without a finite limit. There's no upper boundary. For this first sum, we saw that the upper boundary was 62.5. Down here, this series is going to grow without bound because the common ratio of 4, that exceeds 1. So every term that you add is going to be more than the previous term. And generally, you can show that for any geometric series, if the ratio is greater than 1, the current term is larger than the sum of all of the terms before it. Like 12 is more than 3 plus 3/4. 48 is more than 12 plus 3 plus 3/4. 192 is more than 48 plus 12 plus 3 plus 3/4. And what's 4 times 192? 4 times 192 is 768. So that 768 is more than all of the terms that come before it in the series. So that's why this series is going to be divergent, because every term is at least 4 times greater than everything that's before it. And in the previous example, it works the other way, where 50 is more than the sum of all of the terms that come after it. Now, if you added it up to infinity, A2 through A1 million is going to be less than 50 if you add up all of those terms, because the ratio is less than 1. So with those 2 facts, we can come up with a rule that we call a geometric series test. So a geometric series in the form of n equals 1 to infinity of a to the Rn or a to the Rn minus 1, a just can't be 0. Remember, if you're dealing with a geometric series, you have to be multiplying the same number over and over again. A can't be 0, and generally a should not be 1 either. This series is going to be convergent if the ratio is less than 1, and the series is going to be divergent if the common ratio is greater than or equal to 1. So, well, in absolute value. So if we had like negative 2/3 to the n power, since 2/3 in absolute value, negative 2/3 in absolute value is less than 1, that series would converge. So when we look at our examples, we're just going to determine if the series is convergent. If the series is convergent, we're going to find the sum of the series. And here is the formula that we're going to use to find the sum of that series. We're going to have S equals A over 1 minus R. It's a pretty straightforward process. So all we have to do is identify the common ratio and the first term of the series. So now the key thing is paying attention to the value of n that the series starts with. In this case, for example, 1, n equals 1. So we know that A1 is going to equal 3 times 4/5 to the first power, which is just going to be 12 over 5. So we know our R is equal to 4/5. And since 4/5 is less than 1, we know that our geometric series is going to be convergent. So since the series is convergent, we can use this formula S equals A over 1 minus R. Now, A is just the first term of the series. So in this case, our sum, we'll just say sum out to infinity, is going to be 12/5 over 1 minus 4/5. And that's going to give us 12/5 over 1 minus 4/5 is 1/5. And so you could say we're doing, you can cancel the 5s out and you'll just get 12, or you have 12/5 times 5 over 1, which is still going to be 12. Either way, out to infinity, this sum is going to equal 12. For example, 2, we have 3 to the n over 1,000. Now, the first thing I would do is rewrite this so that it's the sum from n equals, now pay attention to n being 0 in this case, so n equals 0 to infinity. I would take out the things, separate the n's from the terms that do not have an n. So we'd have 1 over 1,000 times 3 to the n. So this 1 over 1,000 doesn't matter. It's as good as if it was in the front of the sum. And so another rewrite you could do is just the sum from n equals 0 to infinity. We'll put the 1 over 1,000 in the front, and we just have 3 to the n. So in this case, A1 is still going to be the first term of the series, but we're starting with n equals 0. So A1, well, just the first term of the series, is going to be 3 to the 0, which is 1 times 1,000. So we get 1 over 1,000. Now, since R equals 3, and that's greater than 1, our series is going to be divergent. And that's it. So it has no sum because it's divergent. For example, 3, we have 8 plus 6 plus 9 halves plus 27 over 8. And we want to know if this series is convergent or divergent. So if you're given the sums of a bunch of different terms, to find the common ratio, you should do like 6 over 8 or 9 halves divided by 6 or 27/8 divided by 9 halves. So we're going to do 6 over 8, and that simplifies to be 3/4, and that's going to be our common ratio. So another way we could write this is the sum from n equals 1 to infinity of 8 times 3/4 to the n minus 1. So if we're looking at it this way, then we know still A1 is 8. So this series is convergent because the common ratio of 3/4, that's less than 1. So we're going to have the sum is equal to the first term, which is 8 divided by 1 minus 3/4, which is 8 divided by 1/4, which equals 32. So we took what was a sum and just expressed it as a proper sum. Like we took this string of terms and turned it into a proper sum like this. And again, we could find this common ratio by dividing any two consecutive terms right divided by left. So if we done 9 halves divided by 6, we would get 3/4. Or if we done 27/8 divided by 9 halves, we would still get 3/4. So if you're given a sum, as long as you divide consecutive terms, you get your common ratio, which again turned out to be 3/4, which makes this series convergent. And then we found the sum by doing A divided by 1 minus the ratio, which gave us 32. For example 4, we have 4 over 2 to the n. And again, we're starting with n equals 0. So my recommendation is you put the 4 in front of the sum. So we're going to have n equals 0 to infinity. And then what's left over would be 1 over 2 to the n power. So an easy rewrite on that is you have 4 times the sum from n equals 0 to infinity. And since 1 to any power is 1, I would just make this 1 over 2 to the n. So we know r equals a half. And so that's going to imply convergent. And we know the first term of the series is, so if n, now again, paying attention to what n is going to be important for identifying the first term. So 1/2 to the 0 is going to be 1 times 4. So we're just going to have 4 as our first term. So our sum is going to be a, which is 4 divided by 1 minus a half, which is going to be 8. So this series is convergent, and it converges to a sum of 8, or its limit is 8. And finally, for example 5, we're starting with n equals 1, and we have 1.075. 1.075 is greater than 1, which is going to imply divergent. So quickly, that concludes this video over geometric series. Now again, a geometric series is going to be convergent if the ratio is less than 1, is going to be divergent if the common ratio is greater than or equal to 1. In a follow-up video, we're going to work through the AP practice questions that you can expect to see on the augmented AP exam. I would recommend going through that with me as well. I'll see you guys in that video.